Thanks. Well, good morning. We were talking about elasticity last time, and I got up to the last part, which was the different ways to measure elastic properties. So I'll finish that, and then we'll get as far as we can through thermal expansion. These first couple lectures seem to be a little bit longer than the next few, so we'll catch up in the next week or so. But the common ways to measure elastic properties like Young's modulus, shear modulus, and Poisson's ratio. There's basically three ways: a dynamic resonance technique, a velocity of sound technique, and the static technique, which we sort of described, where you generate a stress strain curve. So the dynamic resonance and the velocity of sound, they're adiabatic. The strains are extremely small. You're not really stressing the material. You're either vibrating it or measuring the velocity of sound through the material. So adiabatic means there's no heat exchange with the surroundings. In the static test, you're actually putting a sample in a mechanical test machine and loading it. So there's large strains, it's isothermal. During the test, heat is exchanged with the surroundings. So when you measure materials under adiabatic conditions, like dynamic resonance and the velocity of sound, they're going to have higher elastic constants than when measured under these isothermal or static conditions. When you stress material, it's going to give a slightly smaller value for the elastic properties. So refractories also experience time-dependent deformation. There's creep, silicate phases can flow. You have microcracks that can open or close. So they're all going to affect the modulus and give a lower value. So any of these mechanisms, creep, viscous flow, opening and closing of microcracks, they're going to yield lower values of elastic properties than under these isothermal conditions. Actually, under isothermal conditions alone, they just add into the lowering of the elastic properties. So for dynamic resonance, you're just vibrating a material at its natural resonant frequency. And if you're looking for the Young's elastic modulus, it's going to be a flexural vibration. If you're looking for the shear modulus, it's going to be a torsional vibration. And there are test geometries that are worked out, usually a rectangular bar or plate or even a cylinder. So the equations are worked out for all these different geometries. And basically, Young's modulus is proportional to the frequency squared, the flexural frequency squared, and shear modulus is proportional to the frequency squared, the torsional frequency. So FF is the frequency in flexure, FT is the frequency in torsion. And how you get each one of those frequencies is depends on how you vibrate the sample. So you can determine Young's modulus and shear modulus, and I gave an equation that related both of those values to the Poisson's ratio. So what you have to do is you measure both of these frequencies, and you have to determine Poisson's ratio, and that's done by this technique, iterative technique. So you have the equations that are worked out for both of these conditions, for vibration and flexure and vibration and torsion. The equations for the flexure for Young's elastic modulus all have Poisson's ratios in them. So you have to start out by guessing a Poisson's ratio, and we said usually 0.1 to 0.2, but let's say you guess between 0.1 and 0.15. You then calculate the Young's modulus. The shear modulus you calculate directly from the torsional vibration. So you have a value for E and G. You use that equation relating EG and nu. You calculate a Poisson's ratio and you compare it to your guess. And if it's not close, you make a change until the two values agree. Then you have all three values, EG and nu. It sounds messy, but it's not that complicated. So you're putting in these standing waves in these different sample configurations. So this would be a plate. This is a torsional vibration. This is a flexural vibration. So the dotted lines are the nodal points where there's no vibration. It forms an X on this plate in torsion. And then the nodal points in flexure are these two dotted lines. So this curved line is how a half a wave is vibrating, and then it is moving up and down, and the dotted line shows it in the upper position. And same thing here, you can see this vibration goes from one corner to the other corner and then up and down. So L is a sample length, N is an integer, and lambda is the wavelength. So L equals N lambda over 2. So to get a torsional vibration, you have to have a driver in a corner and a detector in an opposite corner. To get a flexural vibration, you have a driver at the end in the center and a detector at the other end in the center. So there's multiple ways of driving the vibration. You can use a piezoelectric transducer. You can take a small hammer and strike it at that position, and that's impulse excitation technique. And then you can use a microphone or another piezoelectric transducer as the detector. And you can also do this type of measurement at temperature. So you have to put the sample in a furnace, and you hang the sample by high temperature wires, Cantho wires, platinum wires. And so for the flexural vibration, you wrap the wire around the end of the sample, and it comes up from the center point outside the furnace. So outside the furnace, you have a driver and a detector. And if you're doing torsion, you put the you hang it so that the wires are towards the edge at the end. So you have a driver and a detector. So you can put these samples, hang them in a furnace, and slowly heat them and watch the vibration change as a function of temperature and measure the decrease in these properties as the temperature increases. The velocity of sound measurement, you just determine the velocity of sound in the sample. We mentioned the strength of the atomic bonds, the density of the atoms determines the elastic modulus. Well, it also determines the velocity of sound. So the higher the velocity of sound, the higher the elastic modulus. So there's two ways to do this. There's a transit time technique and a pulse echo technique. So in the transit time, you just measure the time it takes for a sound wave to travel one length of the sample. And then in the pulse echo technique, the sound wave goes through the sample, bounces off one end and comes back. So you're measuring twice the length of the sample for that sound wave. So the wave is reflected from the free surface. So the first technique looks like this. The transit technique, you have a transducer on one end of your sample, and it can be in any shape. Doesn't matter if it's a rod or a plate. You have a driver transducer, you propagate a sound wave, and you have a pickup transducer. So that's the transit technique. The pulse echo technique, you just have one transducer that's both the driver and the pickup. You transmit a pulse, it reflects off the back surface and comes back. And then there are various ways you can make high temperature measurements with this technique. So here's a simple approach. Here's your sample, and you basically notch the sample. So you put this end of the sample, the notched end, in the furnace, and then your driver and pickup transducer is sitting outside the furnace. So this is a pulse echo technique. So you're actually having a length here and a second length. So the sound wave hits this side, this ledge here, and comes back. The same pulse hits this one, the far end that's in the furnace, and comes back. Actually, both ends are in the furnace, but you're going to get 2 times. And the difference in those 2 times is going to be the time for this pulse in this smaller region. So the velocity of a longitudinal sound wave. So you have transducers that create longitudinal sound waves. You have transducers that create shear sound waves. So you need 2 types of transducers. So a longitudinal sound wave, that velocity that you measure, VL, is going to equal 1 over the density rho. And then there's 2 elastic moduli here. K is the bulk elastic modulus, and G is the shear modulus. I didn't define K, but K is the change in volume as you apply uniform pressure. So V times dV is the bulk elastic modulus. You're actually not measuring it in this experiment. You're just going to calculate it. So the longitudinal velocity is going to be a function of density, bulk elastic modulus, and shear modulus. The velocity of a shear sound wave, Vs, is going to give you G directly. So it's just G over rho to the 1/2 power. And this whole term is also to the 1/2 power. So use the following equation to calculate E in Poisson's ratio. You calculate G directly. You can put a G in this equation. You calculate K from this equation. It's the only unknown. So you can get E. You put E and G into this equation and you get nu. So you get E, G, and nu from this type of experiment by just measuring a longitudinal sound wave and a shear sound wave. And then the other method is the static method. And simply you're putting a sample in a mechanical test machine, and usually it's done in compression or bending in flexure. So you generate a stress strain curve. It's that simple. If you're doing modeling of stresses with finite element modeling, you want to use a static modulus. It's going to be a little bit lower, and it's more realistic because it's giving you the moduli under actual loading conditions, and that's more realistic for a vessel where the refractories are under a load. So static methods yield elastic properties closely approximating those in an actual refractory vessel. So people like to use the static values when they're doing finite element analysis. Again, flow of silicates, shrinkage of pores, closing of microcracks at low temperatures, plastic deformation at high temperatures. are all going to lower the elastic moduli. So here's a cylinder in compression and a bend bar in flexure. So you apply a force to the ends of the cylinder, shrinks by delta L. So the equations are real simple. The stress equals the force over the area, the strain equals delta L over L, and then Young's modulus simply equals stress over strain. And in a bend bar, you have to measure the deflection at the midpoint of the bend bar. So when you apply a stress to a bend bar, the stress equals 3F, which is the force, L is the span, and it's 2BH squared. H is the height of the sample, and B is the width. And then the deflection, delta is over here in this equation. This is really the slope of the stress strain curve, force over delta. So L, B, and H, they're all the span and the sample dimensions. You have the force and then the deflection. So you have to put some type of extensometer on here and measure this deflection accurately, so you can get E directly. So that's the two methods that where you would put a sample in a mechanical test machine and get a stress strain curve. So very simply, stress and strain at room temperature, you're pretty much going to have a linear elastic type behavior. But as you go to higher temperatures, the curves are going to start to bend over. And usually you take the tangent at the origin here as the elastic modulus. So E or G are both going to decrease as the temperature increases. So those were the three techniques to measure the elastic properties. So those properties are important for thermal shock, which we'll discuss those theories for thermal shock in a couple of weeks. But we also need to do a section on thermal expansion, and I'll define thermal expansion. The origin of thermal expansion relates to bonding and potential energy. We'll look at how the different aspects of the structure affects thermal expansion. We'll look at some typical refractory materials, and then how you measure thermal expansion. So A is the coefficient of linear expansion. It equals dl dt divided by L. So L is the length and T is temperature. So the change in length basically divided by the change in temperature. So the units are either centimeters per centimeter degree C. The length units always cancel, so it's 1 over degree C, or you can do inches per inch per degree F. The inches cancel, and it's just 1 over degrees F. So that is your linear thermal expansion coefficient. A simpler way to look at it, A just equals the final length minus the initial length divided by the initial length and the difference between the final temperature and the initial temperature. So LF is the final length, L0 is the initial length, TF is the final temperature, and T0 is the initial temperature. And again, units are 1 over C or 1 over F. So you measure the change in the length of the sample as you change the temperature. So that was in one direction, the linear expansion coefficient. There's also a volume expansion coefficient, and that's alpha. So that's dV over VDT. So we're looking at the change in volume as we change the temperature. So the units here are cubic centimeters per cubic centimeter degree C, or again, just 1/degree C, or cubic inches per cubic inch degrees F, or just simply 1/degrees F. So that's the volume expansion. What you're usually measuring in the lab is a linear expansion. So refractories are basically isotropic materials. They're polycrystalline. There can be multiple types of crystals, multiple types of phases. They can have glass present, but even if they're polycrystalline, the arrangement of the crystals are random. So refractories are basically isotropic materials. So in that case, you can relate the linear coefficient A to the volume coefficient alpha. So V plus dV, so the volume plus the change in the volume equals L plus dL, and it's isotropic, so you have three directions, X, Y, and Z, so it's cubed. So V plus dV equals L plus dL cubed. And dV is just alpha V dt, and dL, we just define these as AL dt. We factor out the volume and L cubed, and they cancel. L cubed equals the volume. So you have 1 plus alpha dt, and then you expand this term here. It's 1 plus 3a dt plus 3a squared dt squared plus a cubed dt cubed. These linear expansion coefficients are small numbers, something times 10 to the minus 6. So when you cube that over here or you square it over here, it becomes an extremely smaller number. So these two terms basically are close to zero, so you can ignore them. So you just end up with 1 plus alpha dt equals 1 plus 3a dt. The ones cancel, the dt's cancel. So alpha just equals 3 times a. So for an isotropic material, the volume expansion coefficient just equals 3 times the linear expansion coefficient. So for the origin of thermal expansion, we have to look at the atomistic viewpoint. So thermal expansion simply corresponds to an increase in the interatomic separation distance as you increase the temperature. We looked at this for, we looked at the potential energy well, we looked at the elastic modulus. So real materials have asymmetrical potential energy wells. But we'll look at two cases here. We'll look at an atom that's vibrating in a symmetrical potential energy well, and one that's vibrating in the real situation in an asymmetrical potential energy well. The first case gives rise to no thermal expansion. The second case gives rise to a thermal expansion. So this is an atom vibrating in a symmetrical potential energy well. It's basically a harmonic oscillator. So we saw this type of plot before last class, potential energy versus interatomic separation. And this represents a symmetrical potential energy well. The minimum here is the equilibrium position at 0 degrees K. And then as we increase the temperature from T1 to T2 to T3, so T3 is greater than T2, it's greater than T1. The red arrows represent the amplitudes of vibration. So we're increasing the temperature, the atom is vibrating about this equilibrium position. So increase the temperature, we're increasing the energy, we're increasing the amplitude of vibration. But if you notice the midpoint by these vertical bars, the midpoint of each vibration is always the same. Since it's always the same, there's no thermal expansion. So the interatomic distance R is always the same, it's constant. So real materials do not behave like this. But if this were the case, if we had a material that exhibited no thermal expansion, when you heat it up, it would not generate any thermal stresses, and you wouldn't have a thermal shock issue. But unfortunately, real materials do not behave like this. Uh, they have asymmetrical potential energy wells. So let's take an atom vibrating in this asymmetrical potential energy well. That's an anharmonic oscillator, and ionic crystals, covalent crystals uh, follow this kind of behavior. So the potential energy E equals the sum of these two terms, the Coulombic attraction term and the overlap repulsion term. We had this equation last class for the asymmetrical potential energy well when we looked at the elastic modulus. So E is the potential energy, R is the interatomic separation distance, A, B, N, and M are constants, and N is usually around 1, and M is usually between 3 and 10 for ionic crystals. All the metal oxides that make refractories are ionic crystals. So minus A over R to the N is the Coulombic attraction. So this is the attractive term. And the repulsive term is B over R to the M, the overlap repulsion. So potential energy versus interatomic separation. The top line again is the repulsive energy, the top dotted line. And then this bottom dotted line, which eventually becomes solid, is the attractive term. And the sum is the solid line, the potential energy well. The minimum here, again, is the equilibrium position at 0 degrees K. So now we heat it up from T1 to T2 to T3. So T3 is greater than T2, it's greater than T1. So now we're increasing the temperature, we're increasing the energy, we're increasing the amplitude of vibration. So if you look at the midpoints of these vibrations, as we increase the temperature, you see them shifting to the right. So the midpoints are moving to the right, and the interatomic distance is increasing, and that's why we have thermal expansion, simply because as we heat it up, the interatomic distances, the average distances are increasing with temperature. And that's because this is not a symmetric potential energy well. So this is how real materials behave. And so therefore we have to worry about thermal expansion generating thermal stresses during thermal shock. So thermal expansion due to the asymmetry of the bonding forces between the atoms cause the atoms to move apart because the potential energy well is not symmetrical. It basically takes a lower force to separate the atoms than to bring them together. So that's the source of thermal expansion in our refractory materials. So some of the structural aspects of thermal expansion, we'll look at bonding. We'll consider single crystals, and then polycrystals, and then glasses. So refractories are a combination of polycrystalline phases and amorphous glasses. So for the bonding, there's ionic bonding, covalent bonding, metallic bonding. So relative to ionic bonding, and that's our metal oxides like MgO, Al2O3, and so on. There's actually 6 metal oxides that make up all of the refractory materials. So relative to the metal oxides, the ionically bonded materials, covalent materials like the carbides and nitrides, silicon carbide, silicon nitride, the covalent bonding is much stronger. They have greater attractive forces, so they're going to have lower thermal expansion coefficients. So carbides and nitrides lower thermal expansion coefficients than the oxides. And it's a pretty big difference. Like silicon nitride is 1/3 of MgO, an oxide. So these stresses that are generated during thermal shock are much lower when you have carbides or nitrides present. And then metals, which we're not really dealing with, but metals have weak attractive forces, so they're going to have a higher thermal expansion than the oxide materials. The melting point is related to the chemical bonding, the strength of the chemical bonds, and so the melting point is basically a measure of the attractive forces. So the higher the melting point, the lower the coefficient of thermal expansion. So high melting point materials have deep potential energy wells and also narrow potential energy wells. So just looking at a couple examples here, I've listed some metals, lead, aluminum, copper, iron, and tungsten. And then I have a list of the thermal expansion coefficients. These are times 10 to the -6 and per degree C. So this would be 28 times 10 to the -6. So we go from 28 to 24 to 17 to 10 to about 4. So going from top to bottom, the coefficient of thermal expansion decreases. And then the temperature in degrees C from top to bottom increases. So 327, 660, 1083, 1537, 3407. So higher melting materials have a lower coefficient of thermal expansion. And the asterisk just means these are the values at room temperature. So alkali halides, lithium iodide, lithium bromide, lithium carbide, and lithium fluoride. This is again times 10 to the -6 per degree C. 90, that's really high. 50, 43, 34. The alkali halides have very high thermal expansion coefficients. So they go from 90 down to 34, and then the melting points go from 450 to 547 to 614 to 842. So the same trend here, decreasing coefficient of expansion, increasing melting point. And these are typical values of the coefficient of thermal expansion for some ceramic materials. The first three are refractory materials: alumina, magnesia, and zirconia. Now the asterisk here, this is an average thermal expansion coefficient from 0 degrees to 1,000 degrees C. So it's the average slope of the delta L over L versus temperature curve. Again, these are all times 10 to the -6 per degree C. Alumina 8.8. MgO is one of the highest expansion materials for the refractories. It's 13.5. Zirconia is 10. And the thorium oxide is 9.2, and your uranium oxide is 10. So the first three are refractory materials. And MgO having the highest thermal expansion coefficient is going to have the biggest problems for designing a material that resists thermal shock because of the high thermal expansion. And then I have some typical values for carbides and glass: silicon carbide, titanium carbide, and boron carbide. These are again averages from 0 to 1,000 degrees C, and they're all times 10 to the -6 per degree C. So silicon carbide is 4.7. That's about 1/3 of MgO. Titanium carbide is 7.4, and boron carbide is 4.5. Silicon carbide is used a lot in refractory, so it has a pretty low value of thermal expansion. So it's going to have less severe problems in terms of thermal shock. And I put that in glass here because silicate glasses are present in a lot of refractories, especially the fire clay, low alumina type materials. So this is just a window glass, a soda lime silicate glass. It's typical of all glasses, about 9.0. So it's pretty close to a material like alumina. And I've also listed the amorphous form of quartz, SiO2, fused silica. Its structure is such that it has a very low thermal expansion coefficient, 0.5. So that's really low. This material exhibits great thermal shock resistance up to about 1,200 degrees C. And unfortunately, when it hits that temperature range, it crystallizes back to uh, cristobalite or perhaps even trinamite, but usually cristobalite. So the high temperature crystalline form of quartz. So that's too bad because this would be a great material, would be an acidic type refractory, would be a great material for thermal shock resistance, but it's only useful to about 1,000 degrees C or so. So we'll just look at single crystals for a few minutes. So in a single crystal, the thermal expansion is going to be different in different crystallographic directions. So different expansion coefficients as a function of the direction. So there's these 6 classes of crystals: cubic, tetragonal, hexagonal, triclinic, orthorhombic, and monoclinic. You only need one linear coefficient of expansion for a cubic material because it's isotropic. For tetragonal and hexagonal crystals, you need 2 coefficients. It's anisotropic. And for triclinic, orthorhombic, and monoclinic, you need 3 expansion coefficients. It's also anisotropic. So these are those unit cells, the 6 different crystals. There's cubic, tetragonal, orthorhombic, monoclinic, triclinic, and hexagonal. So all of these crystals have a atom at the corners of whatever shape they're in. They're called primitive. If there's an atom in the center, it's body centered. If there's an atom on the face, it's face centered. If there's an atom on opposite faces, it's called base centered. So these are the different possible single crystals and the location of the atoms. And the diagrams show their shapes. And for the notation, we have an X, Y, Z coordinate system. A, B, and C are the lengths of the unit cells along those 3 axes. And alpha, beta, and gamma are the angles. So if we look at these systems, cubic, hexagonal, tetragonal, orthorhombic, monoclinic, and triclinic, these are the number of lattices in each system. And then we have A, B, C, and alpha, beta, and gamma defined for each system. And then this column is how many lengths and angles you need to specify for each one of these systems. So, for example, cubic, A equals B equals C, and all the angles, alpha, beta, and gamma, are 90 degrees. So you just have to specify the length A, because A equals B equals C, and all the angles are 90. So you just need that one length to specify a cubic crystal. And orthorhombic, A, B, and C are different, but they're all the angles are 90 degrees. So you have to specify A, B, and C. And for example, triclinic, all the lengths are different. A does not equals B, does not equal C, and all the angles are different. So alpha does not equal beta, does not equal gamma. So you have to specify the 3 lengths and the 3 angles. So the thermal expansion depends on the direction in these single crystals. And so there's different expansion coefficients in different directions. And the reason I want to go over the single crystals is because they eventually form polycrystals, and there's going to be thermal expansion mismatches at the grain boundaries between the crystals, and that's going to generate micro stresses and then micro cracking. So cubic, you just need one dimension, one expansion coefficient. It's isotropic, so alpha, the volume coefficient, equals 3 times the linear coefficient. So alpha equals 3 times A. For tetragonal and hexagonal, you need 2 expansion coefficients. So the volume coefficient equals 2 times, we'll call this A in the A direction plus A in the B direction. And triclinic, orthorhombic, and monoclinic, you need 3 coefficients. So alpha equals A sub A plus A sub B plus A sub C, because the A's are different in the 3 different directions. For these 3, and the A's are different in 2 different directions for these 2. So a simple example of this, this is hexagonal graphite, crystallized carbon. So graphite forms these layered plate-like structures. So the atoms are the black circles. So these are 6 carbon atoms per ring here, these hexagonal rings. So the rings form these plate-like structures that's known as the basal plane. Carbon has covalent bonding, so the bonds within these layers are extremely strong. So that means in that plane of the layers, it's going to have low thermal expansion. But the bonding between the layers is very weak. So that's the C-axis in this direction, and the A-axis is, well, both axes are in the plane of these hexagonal rings. So these are values that are average from room temperature to 800 degrees C. So A perpendicular to the C-axis. So that's A in the direction of these planes is only 1 times 10 to the minus 6 per degree C. So very strong bonding in the planes gives very low thermal expansion coefficient. But then A parallel to the C-axis in this direction, that's 28 times higher, 28.3 times 10 to the minus 6 per degree C. So graphite is very anisotropic, strong covalent bonds in the planes, weak van der Waals bonds between the planes. So that's an example of very anisotropic thermal expansion material. So some other hexagonal materials that are anisotropic, alumina. So this is A perpendicular to the C-axis and then A parallel to the C-axis. It's not that different, 8.3 and 9. Aluminum titanate is actually minus 2.6, then plus 11.5. So some of these materials, and like calcium carbonate is another one with a negative expansion in one direction, have a unique crystal structure, that there's open spaces. So sometimes when atoms are vibrating between in these open spaces, they're actually pulling other atoms closer together. So that gives rise to some negative values here. So even though aluminum titanate is slightly negative in one direction and is considerably more positive in another direction, overall it's a positive thermal expansion. So alumina is an important refracting material. So is mullite, 3Al2O3, 2SiO2. It's 4.5 and 5.7. TiO2 is an impurity, usually in refractories. It's 6.8 and 8.3. And this is zircon, another refractory material. That's a little bigger difference here, 3.7 and 6.2. And then calcium carbonate, that's half of the raw material for dolomite. The other half is the magnesium carbonate. It's really different, minus 6 and then 25. So for polycrystalline materials, um, you can consider them to be isotropic, even though they're made up of all these different types of single crystals. They're random, so they average out to give you an isotropic material in terms of thermal expansion. So you can say that the volume thermal expansion coefficient equals 3 times the linear expansion coefficient. This would be true for most polycrystalline refractory materials. Again, they're consisting of single crystals of maybe more than one type of crystal plus glassy phases, and they're random. However, sometimes when you process a ceramic material or refractory material, you can introduce some texture on the microstructural level. So if you have grains or aggregates that are irregular or non-spherical, they may align in some preferential direction during the processing. So you can extrude refractories, you can press refractories. Um, so the thermal expansion of products produced by extrusion can differ in directions parallel and perpendicular to the extrusion direction. So maybe you're extruding a fire clay refractory. The clay has a structure somewhat similar to graphite. They're platelets. So they're flat plates. They tend to align in the extrusion direction. So you introduce some texture into that material. And then in the pressing direction, the same thing. Thermal expansion of products produced by pressing different directions parallel and perpendicular to the pressing direction. So if you're pressing a composite material with like MgO with the flake graphite, we just saw the layer structure in crystalline crystalline carbon, which is graphite. They will align perpendicular to the pressing direction. So you can introduce texture in a couple different ways in refractory materials. So they may not exactly be isotropic. So you would have to measure the thermal expansion coefficient in the different directions. So comparing isotropic and anisotropic materials, isotropic materials, no microstresses develop due to expansion effects during heating and cooling cycles. And anisotropic materials, you can develop microstresses due to expansion effects as the material is heated and cooled. When you develop stresses, you'll develop microcracks. Assuming the microstresses are large enough, stronger than the grain boundaries, you'll develop these microcracks. And microcracks form, they create fracture surfaces that takes energy away from the stored elastic strain energy in the stress field, and you relieve the stresses. So this is a very simple microcracking model. So we have a grain 1 and a grain 2. The change in temperature because of the expansion mismatch between the two grains creates these normal stresses. So we'll consider the normal stress sigma n at this grain boundary. And when sigma n reaches the fracture strength of this grain boundary, you form a microcrack. So we go from stress-free, we apply a temperature difference, it's stressed, and if that temperature difference creates a large enough sigma n to reach the fracture strength of that grain boundary, we have a microcrack. So this normal stress sigma n between these two grains 1 and 2 just equals the difference in the thermal expansion coefficient between N1 and N2 times the elastic modulus times delta T. So the difference in thermal expansion times delta T is your strain. And we know the stress equals a strain times Young's modulus E. So it's a very simple approach. E is Young's modulus, delta T is a temperature difference. So the bigger the thermal expansion difference, the bigger the stress that develops as a function of temperature. So that's how refractory materials are microcracked. Most every refractory is going to have microcracks because of the difference in thermal expansion and the different directions in the crystals. So what happens when you heat and cool a material like this, and this is an example for polycrystalline TiO2, it's hexagonal. I just showed that in one of the previous tables. There's a difference in the thermal expansion coefficient and the two different directions. So if you have expansion versus temperature, as you heat and cool this, microcracks are going to open and close. So we start out at the sintering temperature. We start out with the powder compact, and we just press it. We bring it up to temperature. We sinter it. We densify it. So we have a strong, coherent body at this high temperature for TiO2. So right at the firing temperature, we develop a very dense, coherent structure. But then we cool it back down. So we have normal thermal expansion behavior. And then at some point, because of the temperature difference and the thermal expansion coefficient difference, we start to form microcracks. So they open up and it changes the slope. It gives a lower apparent thermal expansion. So on the cooling curves, the microcracks form, they relieve the stresses. TiO2 is the body of the material is still contracting, but the microcracks are opening. So that changes the slope, makes a lower apparent coefficient of thermal expansion. Keep going the wrong way. So now we're back at room temperature. We have open microcracks, and then we heat it back up to the sintering temperature. And at some point, as we're heating it, the microcracks are closing. And at this point, they're completely closed. And we have a steeper slope here, a higher thermal expansion coefficient. So on the heating curve, the TiO2 is expanding, but the microcracks are closing. That gives that lower slope, the lower apparent coefficient of thermal expansion. So this is what's happening when you develop microcracks, when you do an expansion temperature curve. It turns out the microcracking is a function of grain size. So if you have extremely fine grain sizes, you may not develop microcracks. So this is expansion versus temperature for magnesium titanate at 3 different grain sizes, 1 micron, 5 microns, and 15 microns. So there's generally a critical grain size where we have microcracking in this hysteresis cycle. Refractory materials are usually coarse grained, so you're usually going to have this hysteresis type behavior. So we can derive a very quickly an equation to describe this. The development of microcracks can be related to the grain size, and that's we'll call the grain size L. We'll use an energy balance approach to look at this. We talked about elastic strain energy, the stored elastic strain energy. So SE is the average strain energy per unit volume. And then L cubed is the volume. So L is the grain size, but L cubed is the volume of the grain. So when we form microcracks, those cracks have a certain fracture surface energy, that's gamma F. So gamma F is the fracture surface energy per unit area, and the area would be L squared. L again is the grain size. So the total energy of this system, TE, equals this first term, SELQ, minus the energy that's converted to the fracture surfaces, gamma FL squared. If we take the first derivative of this equation, set it equal to 0, we have this equation, so dTE over dL equals 0, 3SEL squared minus 2 gamma FL. At this point, at 0, we have the critical grain size for fracture or for microcrack formation. Solve for that. So L critical equals 2 gamma F over 3 SE. So this is the critical grain size for microcrack formation based on an energy approach. We can measure the fracture energy. We can calculate the stored elastic strain energy. So we should be able to figure out these critical sizes. And I put in glass because a lot of refractories are going to have, basically all refractories have some glass present, some silicate glass. Clay-based fire clays have a substantial amount of glass present. So I thought I'd show the expansion behavior for a glass. This is the change in length versus temperature. Glass goes through a transformation temperature, so it's a brittle material in region 1 here. At some point, the temperature is high enough, the glass starts to reconfigure itself, and the expansion increases. So this slope increases above the transition temperature. And then at some point, glass softens, and this is measured in a push rod dilatometer. There's a slight force on the sample. So as soon as it becomes plastic, it'll deform under that load. So region 1 is from room temperature to the transformation temperature. That's this region here. It's normal linear expansion. But then in region 2, between the transformation and softening temperatures, you have a combination of these configurational changes and thermal expansion. So you have the thermal expansion contribution, but you have configurational changes. The temperature is high enough so the glass structure is reconfiguring and expanding. And then above the softening temperature, the material becomes viscous and it starts to flow. And again, if it's measured in a push rod dilatometer, there's a slight force on the sample, so it's going to decrease in size. So we'll look at relative ranges of thermal expansion, some typical values for refractories. Some refractories exhibit phase transformations. So there's some drastic changes in thermal expansion at certain temperatures. And we'll look at the anisotropy and how that relates to microcrack formation. I don't think we'll get through all of this, but maybe the first 3 here today. So relative ranges of thermal expansion coefficient for the materials that we're interested in. Low values are 0 to 4 times 10 to the minus 6 per degree C. Fused silica, we mentioned, it's useful, let's say 1,000, maybe 1,200 degrees C before it crystallizes, and then it has a high thermal expansion coefficient. Cordierite is a magnesium aluminosilicate. It's another low expansion material, but it's not very refractory. Its useful temperature range is maybe up to 1,200 degrees C, far lower than what we need for a refractory material. And then silicon nitride is also low. It's a little less than 4, and it's stable to high temperatures under inert atmospheres. A medium expansion might be 4 to 6 times 10 to the minus 6 per degree C. Some good materials here are mullite, zircon, and silicon carbide. And mullite is especially important in the aluminosilica systems because it does have a much lower thermal expansion coefficient than a material like alumina. It's about half. So mullite is pretty good in thermal shock. And then anything greater than 6 would be considered high, 6 times 10 to the minus 6 per degree C. Alumina, magnesia, calcia, phosphorite, which is a magnesium silicate, uh, spinel consists of alumina and MgO, and zirconia. Um, these are all pretty high, but they're all very good refractory materials. So the coefficient of thermal expansion obviously varies with temperature. Um, and the way they usually report it is as an average over a temperature range, usually 0 to 1,000 degrees C, room temperature to 1,000, room temperature to 1,600 degrees C. So when you're using average values, you have to be aware that they are average values over a large temperature range. So what you can do is you can express these expansion coefficients as a polynomial equation. So the coefficient of linear expansion A equals A0 plus A1 times T plus A2 times T squared. So A0, A1, and A2 are constants. So you measure the thermal expansion for a material like, let's say, MgO, and then you curve fit it. And so you get an equation that looks like this from the regression analysis. So you actually take the experimental data, fit it, curve fit it, and you end up with equations that look like this. And the constants are documented. So you can look up the constants and calculate, and whatever temperature of interest you have, you can see what the actual expansion coefficient is at that temperature instead of just guessing from an average over a large temperature range. So this is percent expansion delta L over L0 versus temperature. So the slopes of these curves are your expansion coefficients. So this is for some simple oxides. So MgO and CaO have the highest thermal expansions here. Vitreous silica is well, at the bottom of this plot. It's very low, but this curve only goes to about 800, 900 degrees C. And again, when you hit 1,000, 1,200 degrees C, it will crystallize and the coefficient of expansion will become high. Zircon is pretty low. Chrome oxide is here, aluminum oxide is here, and then quartz, and we'll talk about this later in a little more detail. Quartz goes through a displacive transformation, so it usually has pretty high expansion, and then when it goes through the transformation, it has a lower slope. So those are some simple oxides, and noting that MgO is the highest of all the refractory materials. This is the same plot for binary and ternary oxides, delta L over L0, 0 to 2, and then temperature to about 2,000 degrees C. This material, this magnesium aluminosilicate, is that cordierite material that I mentioned. It starts to have serious deformation problems around 1,200 degrees C, but you can see on this plot, it's the lowest expansion material. Here's a spinel, a magnesium aluminate. There's another spinel over here. There's another spinel over here. Spinels are quite useful refractory materials. Here's zircon, it's a little bit lower. Here's mullite, it's quite a bit lower. And here's a calcium aluminate. And then this one is phosphorite, the magnesium silicate. There's a magnesium titanate and another calcium silicate. So those are our typical binary and ternary refractory materials. And then these are the non-oxides. Again, it's the same scale, 0 to 2 for delta L over L0, and temperature in degrees C to about 2000. You can see these curves are shifted downward. Here's boron nitride, aluminum nitride, silicon carbide, boron carbide, and titanium carbide. Here's where iron is quite a bit higher. Graphite is down here. So crystalline graphite, parallel and perpendicular to the basal plane. So parallel is going to be lower, perpendicular is going to be higher. And then we have vitreous carbon. So carbon is an interesting material. It can be completely glass-like or vitreous. As you crystallize it, it eventually becomes graphite. And you can have anything in between from completely amorphous to all different degrees of crystallization to finally complete crystallization in graphite. So these non-oxides tend to be lower, and that's an advantage for thermal shock resistance. So this is delta L over L, and here's another equation of that form where you can do a regression analysis. A plus B, and this is times 10 to the minus 4 times T, plus C times 10 to the minus 4 times T, and that term is squared, and then D times 10 to the minus 4 times T, and that is cubed. The temperature here is in Kelvin degrees K. So here are your constants A, B, C, and D. And the melting point is actually given here in degrees K. But if you have alumina and you want to see what your delta L over L is, and if you want percent, you multiply by 100. You put in these coefficients into this equation, and you can calculate the expansion at any temperature. So here's the simple oxides that I showed, the binary and ternary oxides, the non-oxides, and then graphite. So this table corresponds to these three graphs here. So this is that equation at the top of that table. So delta L is the length change from room temperature, and room temperature in degrees K is 293 degrees K to whatever temperature we want to look at, T. If we divide by 100, we get rid of percent and we go to the fractional change. So that's just delta LT over L at room temperature, and then this equation with our constants A, B, C, and D, and our temperature terms. And if we take the derivative of this, we end up with this equation for the linear thermal expansion coefficient, which is this equation I showed up here. So if we want to calculate the linear coefficient directly, we can use this form of the equation, put in our constants B, C, and D. So that's basically the equation I just showed. A0 would be B, A1 would be C, and A2 would be D. So there's at least a couple different ways of calculating a length change or a coefficient of thermal expansion. And again, all these values are from real experiments and from curve fitting and regression analysis. So we'll just look at a few more curves here and call it a day. These are some typical refractories, so the thermal expansion for different types of refractories. So these are all fired refractories. So they're centered at temperatures higher than that are shown here, higher than 13, 14, 1500 degrees C. I mentioned that MgO was the highest material. So you can see MgO has the highest thermal expansion. I mentioned silicon carbide was low. You can see silicon carbide down here. In the middle are the aluminas. Phosphorite is a magnesium silicate. And then silica goes through a displacive transformation. So pretty rapid increase in expansion as you heat it. It goes through a crystal structure change, and then it tends to level off. So on this plot, MgO tends to be the highest expansion for refractory materials, the hardest to design for thermal shock resistance. Silicon carbide is the lowest, and the aluminas are intermediate. So as you go up in alumina content in the alumina silica series of refractories, you increase the alumina content, you're going to increase the thermal expansion. And then again, there's a phase transformation at about 573 degrees C, a crystal structure change, and a total change from a pretty high thermal expansion material to pretty flat thermal expansion behavior. So a silica refractory in this temperature range, it's hard to thermal shock because it doesn't change drastically with temperature. But you have to get through this part first, so that's the most difficult part. Most silica refractories, if they're in a glass crown, have to be heated up slow to go through that transformation to prevent fracture. Same plot for some other refractory materials. I mentioned zircon was pretty low. Chrome and the fireclays are also very low. And then here's your typical behavior for a crystalline silica. So zircon is on this plot the lowest. Chrome is the highest on this plot. When you make a chrome magnesite refractory, you add chrome to MgO. It helps improve the thermal shock resistance because chrome has a lower expansion. It lowers the expansion of a chrome magnesite material. The fireclays are down in here. They're pretty low. And then again, there's two types of silica refractories here. They go through this phase transformation before they become fairly constant. So I think I'll stop right there, and we'll finish this up next time. And then we'll also start on thermal conductivity. So have a good rest of your day. Hopefully it'll be good. And I'll see you next Tuesday. We'll finish up thermal expansion. I think thermal conductivity is a bit shorter, so we might catch up by next Tuesday. So have a good weekend, and I'll see you next week. Thanks for attending. Bye.
Thank you very much.